Okay, let's get started. I don't have enough time today. I've been so busy working. So not working. I'm not paid, but I am actually building the bot, a Discord bot for EuroPython. So been busy all day and meetings and everything, and yeah, crazy. So let's quickly do chapter 16. Let's read it through. Hopefully it's not too long. Yes, it's like 4 pages, 4 sections. So yeah, cause yeah, I have no life. I still haven't packed. I'm flying tomorrow morning. So yeah, okay, let's do it quickly. Fearless concurrency. So yeah, usually concurrency is something that we scare a lot, but how can we be fearless? Handling concurrent programs safely and efficiently is another Rust major goals. Good. Concurrent programming, where different part of program execute independently, and parallel programming, where different parts of the program execute at the same time, are becoming increasingly important. A small computer take advantage of multiple processes. Now, buy a laptop, you got 8 cores. Quite common. Historically, programming in this context has been difficult and error prone. Rust hoped to change that. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. So memory safety and concurrency actually is the same problem because a lot of times, things will go wrong in either one of them or both of them at the same time. So over time, the team discovered the ownership type system, actually a powerful set of tools to help managing memory safety and concurrence problems. So if you have the management system, if you only have like one ownership, then you actually attack two birds with one stone. By leveraging ownership and type checking, many concurrent errors are compile time error in Rust rather than runtime errors. So error can be avoided at runtime. Therefore, rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, tell me about it. Like async code bug are crazily difficult to debug. Incorrect code will refuse to compile and present an error explaining the problem, which will save you time to debug. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped into production, which is something we don't want. We've named this project of Rust Fearless Concurrency. Ooh, that's the name of the project. Fearless concurrency allows you to write code that is free of subtle bugs and easy to refactor without introducing new bugs. For simplicity's sake, we refer to many of the problem as concurrent rather than being more precisely saying concurrent and or parallel. So we are kind of interchangeably using the concurrent word. If this book were about concurrency and or parallelism, we'll be more specific. For this chapter, we mentally substitute concurrent and or parallel wherever we use concurrent. So, yeah. Many languages are dogmatic about the solution they offer for handling concurrent problem. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure way to share state with between threads. Supporting only a subset of possible solutions is a reasonable strategy for high-level languages because a high-level language promises benefit from giving up some control to gain abstractions. However, lower-level languages are expected to provide a solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. So you can go as high as you want or as low as you want. So you have the flexibility of controlling everything, or you just don't care. You want some kind of abstractions of things. Yeah, the topics we'll cover: how to create threads to run multiple pieces of code at the same time, message passing concurrency, where channels send message between threads, shared state concurrency, where multiple threads have access to some piece of data, the sing and send traits, which extend Rust concurrency guarantee to user-defined types as well as types provided by the standard library. Sync and send. User-defined types as, yeah. Right, okay. So first of all, using threads to run code simultaneously. In most concurrent operating system, an executed program code is run in a process. So each program actually is called a process. And the operating system will manage multiple processes at once. So you can open Chrome, you can open my text editor running Rust at the same time, blah, blah, blah. Within a program, you can also have independent parts that run simultaneously. So each process may be multi-threaded. The feature that run these independent parts are called threads. For example, a web server could have multi-threads so that it could respond to more than one request at the same time. Splitting the computation in your program into multi-thread to run multiple tasks at the same time can improve performance, but it can also add complexities. Because threads can run simultaneously, there's no inherent guarantee about order in which part of your code on different threads will run. So that's one thing that is quite different for async code. This can lead to problems such as race conditions, which threads are accessing data or resources in an inconsistent order. So, one thread changing another thing, the other thread don't know it has been changed, got crazy. So that's race conditions. Deadlocks, where two threads are waiting for each other, preventing both threads from continuing. So something wrong with your wait, that they are waiting for each other, which nobody get anything done. So that's that. Bugs that happens only in certain situations and are hard to reproduce and fix reliably. So I've seen this a few times as well. When running the test in multi-thread, sometimes when we are sharing resources, then the order of running it could sometimes produce some bug that disappear when the order is different. So which is a nightmare. Rust attempt to mitigate the negative effect of using threads, but programming in a multi-threaded context takes careful thought and requires a code structure that's different from that in program running in a single thread. So yeah, things are quite different. Programming languages implement threads in different ways, and many operating systems provide an API language that can call for creating new threads. The Rust standard library use a one-to-one model of thread implementation, whereby a program use one operating system thread per one language thread. So one thread in Rust actually means one operating system thread. It's not always true, because you can also I think Zach gave a talk about that before in PyCon US this year. So yeah, you can watch that talk if you want to know more. There are created that implement order models for threading that makes different trade-off to the one-to-one. Yeah, so good and bad things. Create new thread with spawn. To create new thread, we call thread thread spawn function and pass it a closure. We talked about closure before. Yes, remember that. Containing the code we want to run in the new thread. Example in this, so we have spawn, and then we would have a closure here. We have no parameter for this closure. So we put that in, so there will be one thread. This probably is the main thread, so that's the other thread. So now we want the main thread of a Rust program. So yeah, the order will be scrambled because you don't know which one go first, and so main come first, and then main come first. Most of the time main come first, but then number 5 is the spawn thread. So there's no guarantee of the order. So every time could be different. So if, for example, if we run it, I think it could also be different. Yeah, so it's only spawning 4 because I think it is finished, and then I finished the whole program, I think. Maybe. Let's look at the explanation. So it's different. We are different. So call thread sleep force a thread to stop its execution for a short period of time. So we are sleeping here. Allowing a different thread to run. So when it stops, then this one can. So they basically have to pass over the time. So yeah, so the threads will take turns, so you have to pause, otherwise it won't. But that isn't guaranteed. But it's not the case. It probably would do most of the time, but sometimes it doesn't. It depends on how your operating system schedule the thread. So yeah, it's we don't know. That's the answer. In this run, the main thread prints first, and then pass it, and then, yep. So spawn thread print until I is 9. It only got to 5 before the main thread shut down, because the main thread reached the end, so it shut everything down. So that's why we got this one. So this probably like kind of passing through between the two quite evenly. So, but it could also end up like this if it's run on a different machine. Yeah. Waiting for all thread to finish using the join handle. So, yeah. So this time we kind of stopped the spawn thread prematurely because it's supposed to go to 9, but it doesn't most of the time due to the main thread ending. But because there's no guarantee on the order in which threads run, we also can't guarantee the spawn thread will get run at all. So you don't know which one finished first. We can fix this problem of the spawn thread not running or ending prematurely by saving the return value of thread spawn in a variable. So we put it in the variable. The return type is join handle. A join handle is a owned value. So when we call the join method on it, it will wait for its thread to finish. So you can see how this works. So we call it handle, and then at the end we call handle.join unwrap. So yeah, so this is how it works. So now if you run it, then the main program won't finish until this is finished. So calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that the thread is prevented from performing work or exiting, because we have put join after the main thread for loop. So yeah, so we'll have this. So they run simultaneously, and then until the main thread is done, but still we have to hold on because we're waiting for the other thread to finish. So this is what it is. So if we run it, it will be slightly different as well, but it will also wait for it to finish. So yeah, we are very consistently like passing through. I think it's maybe the web browser's VM works like that. Yeah, and then until it's finished. So the so alternating, but it will wait until the end. What happened when we instead move it before the for loop in the main? So it looks like this. So this time we'll have to wait for the spawn thread to finish before we move into this thread. So this is why it's look like this. And this time is consistent because it's not running at the same time. So this is how we can control where it got finished, where this thread joined back basically. Using move closure with threads. So we would use the move keyword with closure passed to thread spawn because the closure will take ownership of the value used from the environment, thus transforming ownership of those values from one thread to the other. So we've talked about that before. We have to have a look now. We discussed move in the context of closure. Now we will concatenate more on the interaction between move and thread spawn. Closure we pass to spawn take on no arguments. So yeah, I said that earlier. I think we are not using any data from the main thread. The data from the main thread use the data from the main thread to the spawn thread. The spawn thread's closure must capture the value it needs. So how can we move that to the other side? So let's attempt to create a vector in the main thread and use it in the spawn thread, and then we'll have a compilation error. So this is V, and then if we try to use it here, we'll have a compilation error because the closure used V, so it will capture V and then make it part of the closure environment. Because now we use the spawn thread, we should be able to access V inside that new thread, but the thread is still in the main thread, so we have an error. There's so many threads. Rust infers how to capture V, but printline only needs a reference to V, so the closure try to borrow V. Yeah, so this print line. So normally, if it's not on a different thread, this will just get borrowed because we just need to print the value. Yeah. The closer, yeah. So it's just borrowing. And however, that's the problem. Rust can tell how long the spawn thread will run. So it doesn't know how, like, if the reference to v will always be valid. So what if like, you know, the main finished first and then, oh, this is not, like, yeah. So we don't know. We don't know how long we need to live. So that doesn't work. So if Rust allows us to run this code, there's a possibility. For example, you drop it here, right? The spawn thread would be immediately put in a background without running at all. Suppose the spawn thread has reference to v inside, but the main thread immediately drop v, which is here. Then using the, yeah, then we don't have the reference to v, which is, oh no. So we have to add move keyword before the closure. There's one here. We force the closure to take ownership of the variable it is using, rather than allowing Rust to infer which one is borrowed, which one is moved. Everything is moved if we do this. We might be tempted to try the same thing, fixing the code where the main thread could drop by using a move closure. However, this fix will not work because what we're trying to do is disallowed for a different reason. If we move it to the closure, we would no longer call drop because this is in the closure, right? So when this is finished, this will naturally finish. You can't really use drop. Yeah, so you can't use code drop on it. So yeah, so it doesn't work. Yeah, so we have another error. So it's like wrong in a different way. So no, you can't do that. Rust ownership rule have saved us again. We got an error from the code because Rust was being conservative at only borrowing v for the thread, which means the main thread could theoretically invalid the spawned thread's reference. By telling Rust to move the ownership to v to the spawn thread, we guarantee that Rust the main thread won't use v anymore. So only one thread is using v at one time. Yeah, so we are violating ownership if we try to use v in the main thread, because you have moved it, then it's not there. You can't use it. Yeah, so the move keyword override Rust conservative default of borrowing. So it won't borrow. Every ownership is moved if it's got used. Yeah. Okay. Next. I'm a bit hungry actually. I am so hungry. Okay. So go back here. We gotta so chapter 2. Okay, it's not too big. Hopefully. Using message passing to transfer data between threads. So, another approach to ensure safe concurrency is message passing, where threads or actors communicate by sending each other message containing data. So, so that's like actually borrow from Go. Do not communicate by sharing memory. Instead, share memory by communicating. To accomplish memory sending concurrency, Rust Standard Library provide an implementation of channels. A channel is a general program concept by which data is sent from one thread to another. You can imagine a channel in a program being like a directional channel of water, which as a stream or a river, you put something like a rubber duck in a river, so it will travel downstream. So yeah, so that's what it is. Basically, just putting things from one to the other. A channel has two halves, a transmitter and a receiver. The transmitter half is upstream location where you put the rubber duck. The receiver is the lower half where the rubber duck end up being at the downstream. One part of your code call the method on the transmitter with the data you want to send, and the other part checks receiving end of the arriving message. A channel is said to be closed if the transmitter or receiver half is dropped. So it needs two halves. So any half is dropped, then it's done. It's finished. It needs to be closed. Here we'll work up to a program that has one thread to generate value and send them down the channel, and another thread will receive the value and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. Once you are familiar with the technique, you can use channel for any thread that needs to communicate between each other, such as a chess system or a system where many threads perform part of the calculation and send the parts to one thread to aggregate the result. These two are very common thing. I think I already think of some Python thing that do the same thing. A chess system that would be like something like RabbitMQ or something that like the server kind of kind of thing. Or maybe I'm just saying things now. I'm hungry. I don't know what I'm talking about. And yeah, this is kind of happen a lot when you have a cluster of computers. You would do like aggregation at the end to one thread. So it happens a lot in multi-threaded systems. We would create a channel, but do not do anything with it. This one compile because Rust can't tell what type of value we want to send down the channel. So we have a tuple, and then we open a channel. So this is a channel, but it doesn't compile yet. We create a new channel using channel function. MPSC stands for multiple processor, single consumer. In short, the way Rust and the library implement channels means a channel can have multiple sending ends that produce value, so multiple producer, single consumer, but only one receiving end that consume those values. Imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. We start with a single producer for now, but we will add multiple producer when we get this example working. So it will return a triple. The first element is the sending end, the transmitter, and the second element is the receiving end, the receiver. The abbreviation TX and TR, transmitter and receiver, traditionally used for yeah, it's like one of my little thing that also do like this. Also do the both TX RX mode thing. It's for Bluetooth transmitter and receiver. Yeah, so we name our variable as such to indicate each ends. We use a let statement with a pattern that the structure. We will use a let statement with a pattern that the structures the triples. We'll discuss the use of pattern let statement instructions chapter 18. But now, if you do something like that, we can break down whatever that got returned to TX and RX. Let's move the transmitting end into a spawn thread and have it send one string. So the spawned thread is communicating with the main thread. So this is how it looks like. So now we have a spawned thread. This side is doing the TX, so it's sending value, and then unwrapped. So yeah, this will give out an option. I think it may fail, and then it will give you none. Again, we are using to create a new thread that use move to move the TX in the closure, blah blah blah. So it will become a result. Oh, so yeah, it could have errors. Unwrap to panic in the case of an error. Yeah, we should handle it properly in real case, but now we just unwrap it. We don't care. So how to receive it? So receive, we will do it in the main thread. Receive equals to rx.received, and then I also unwrap. We let it panic. It's fine, and then got the received. So it's very simple. Yeah. The receive have actually two methods. Is like receive and try receive. We use received, which will block the main thread's execution and wait until we get the message. Once the value is sent, receive will return it in the result again. When the transmitter closes, read will return an error, and then yeah, we have that same thing. The try receive method doesn't block, but will instead turn a result immediately. OK means that we have received a message. If error, that means that we don't have any message. But it doesn't mean that there is actually an error, just like we haven't received it yet. So using try receive is useful if this thread has another work to do and is silly waiting for the message. We could write a loop that could try receive every so often, hand a message if one is available, and otherwise does other work for a little and come and check again. We have used receive in this example for simplicity, and then we got it like this. Channel and ownership, channels and ownership transference. The ownership rule plays a vital role in message sending because they help you to write safe, concurrent code. Preventing errors in concurrent program is an advantage of thinking about ownership throughout your Rust program. Yes, let's do an experiment to show how channels and ownership work together to prevent the problem. Okay, what are we doing now? We again have a bell in the spawned thread, and after we'll send it down the channel. So again, we have that. We break it down. We move the tx part here. We have the val value, and then print, and then now we send it. Okay, but we have a problem here because who is having val? Because like you send it already, and then like now you're trying to use it again. So question mark, question mark, question mark, question mark. We try to print val after we send it down the channel. Allowing this would be a bad idea. Once the value has been sent, the thread could only modify or drop it before we try to use the value again. Potentially, the other thread modification could cause error as well, or unexpected result. So we couldn't have one thing in two places. However, Rust gives us an error if we try, so it won't compile. Our concurrent mistake has caused a compile time error. The send functions take ownership of the parameter, and then the value is moved. So the receiver and take ownership of it, so we can't use it again. So it also stops error from happening. Sending multiple value and seeing the receiver waiting. So it doesn't clearly show two separate threads that are working together, each other over the channel. So we've made some modifications. So now we can see how it works. So again, create a channel, split it. This one will take the send. Yeah, this one will be sending. So take the send, but there is a vector of messages, and then yeah, it will also sleep because then it will just stop executing for a while, so we can see what's going on, and then we received it. So this time, the spawn thread has a vector of string that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling sleep. And in the main thread, we are not calling the receive function explicitly anymore. So this time, instead, we would iterate over it. We are treating Rx as an iterator. For each value received, we are printing it. So, yeah, you should see the 1 second pause. Do we though? Oh, we can't run it. It's fine. We just trust you. We can tell the main thread is waiting to receive the value from the spawn thread. So multiple producers by cloning the transmitter. Yeah, so again we have this, but this time we want multiple producers. So how are we gonna do that? What we're gonna do is to clone the TX. So it's fine, we can clone it, and then in this spawn thread we would use TX1 because we only move TX1 because it's used here, and then we spawn another thread, and then this one we just use the original TX. So we have two producers. And then I received Rx, which we will receive. So what we're gonna do this time, so more messages for you. Yeah, so you can see scramble up because they just keep coming, and then the receive end just keep receiving them. Pastor, give us 2 threads sending different messages. You will see something that's scrambled. You may see the value in another order depending on your system. This is what makes concurrency interesting and also difficult. Yeah, so you can sleep at a different time. Yeah. So it will be more crazy, non-deterministic. So this is one of the way of doing it is to use channel to send messages between each other. This is how you can do it in one way. So let's go to the next page. It's been half an hour. Hopefully we can finish within another half an hour. Sorry, I'm rushing through because I'm running out of time. It's fine. When we do exercise, we will learn more. Shared state concurrency. So this is another way. Message passing is a fine way of handling concurrency, but it's not the only one. Another method could be for multiple threads to access the same shared data. Consider this part of the slogan from the, again, Go. Do not communicate by sharing memory. Oh, okay. But we are violating that. What would communicating by sharing memory look like? In addition, why would message passing enthusiasts caution not to share memory? In a way, channels in any programming language are similar to single ownership, because once you transfer a value down the channel, you can no longer have that. So only one ownership. Shared memory concurrency is like multiple ownership. Multiple thread can access the same memory location at the same time. So we have seen that before. Smart pointers, yes. Multiple ownership can add complexity because different owners need managing. Rust type system and ownership rules are greatly assessed in getting this management correct. So if you really want to share memory, you can do that. Using a mutex. Oh, now we talk about mutex. Mutex. Okay. To access data one thread at a time. So still, you can, all of the thread can access them, but only one at a time. Mutex is a abbreviation for mutual exclusion. Mutual exclusion. As in, a mutex allows only one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants to access by asking to acquire the mutex lock. This this sounds familiar. Yeah. Yeah, I'm talking about Python now. Yeah, the Python GIL lock. But Python only have one lock that lock everything is a global interpreter lock. But if you want, you can have this mechanism. So someone have tried to change that, so there's no GIL Python. Okay, the lock is a data structure that is part of the mutex that keeps track of who concurrently has exclusive access to the data. Therefore, mutex is described as guarding the data it holds via the locking system. So it's kind of like a bunch of people want to have a look at something, and there's a guard there. It's like, okay, you go, and then they have to go one at a time. They can't just swarm the whole thing. Mutex have a reputation for being difficult to use because you have to remember 2 rules. You must attempt to acquire the lock before you use the data. When you are done with the data, with the mutex guard, you have to unlock, which give back the control, the data, so the other thread can acquire the lock. So whoever have the lock is like, you can access the data, and then once you're done, you have to give it back so someone else can have it. A real-world metaphor for mutex: imagine a panel discussion in a conference with only one microphone. Before panelists can speak, they have to ask for or signal they want to use the microphone. When they get the microphone, they can talk for as long as they want, and then hands the microphone for the next panelist who requests to speak. If a panelist forgets to hand the microphone off, they are finished with it. No one else were able to speak. That would be a bad panel. If management of the shared microphone goes wrong, I mean the host, the panel won't work as planned, which is awful. So yeah, all goes wrong. Management of mutex can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust type system ownership rules, you can't get locking and unlocking wrong. Why? Let's look at it. Let's look at what's going on. The API of mutex. So also, whatever type you can use there, then you can use. So we get we have to use mutex because it's not in the prelude. Mutex new, and then this host 5. Let's mu num equals to m.log, so you have to get the log and then unwrap. So okay, you get it. Now you can access using dereferencing num. So num now host to it, and then now you want to put 6 in it, and then that's what's going on, I guess. So now it's 6, right? Bum, bum, bum. Oh no, it's the data is 6 positioned fourth. I don't know what's this, but yeah, the data is 6 now. So yeah, we also use neo. We use the log method to acquire the log. Call to log would fail if other people are holding the log, so you can't get it. In that case, no one would ever be able to get the log. So we have to chosen to unwrap to have the thread panic. So if someone is holding the log, then panic. In this situation, of course, it's not a very good handling. After we have acquired the log, we can treat the return value, named num in this case, is a mutable reference. So the type system ensure that we acquire log before using the value in M. The type of M is mutex i32, not i32. So we must call the log to be able to use i32 value. Yeah, so it's like here M needs to call the log to use it. So M is mu i32, it's not i32, so we have to unlock. So we have to call log to unlock call log to unlock the value. Yeah, so otherwise if you forget, then you won't be able to access the inner i32 value. As you may suspect, it's a smart pointer, of course. More accurately, the call to log returns a smart pointer that call mute guard. Yeah, that's why after that yeah, you can unwrap and then you can call the dereference. Wrapped in a log result. Yeah, return smart pointer wrapped in a log result. So this is the log result. So we unwrap that, we'll get back that mute guard. Mutex guard. That we have handled with call to unwrap. So mutex guard, smart pointer, implement deref. So that's why we can deref. Yeah, we also have a drop implementation that releases the log. So when it got drop, it will automatically release the log. Yeah, which happened at the end of. So after this, after this, this num, which is the mutex guard, will get unlocked. So that's why we can use it here. We can print out here. Well, in the print line macro, it will somehow do the similar thing and access it. So yeah, we won't risk forgetting to release the log as long as we have put it in a separate scope. After dropping the log, we can print the result and see what's changed. Sharing a mutex t between different threads. So now you see how to actually use it. So we have a again a counter. We have holding the value 0 here. We have a handle, which is a vect and down for 0 to 10. So we've spawned 10 threads. Whoa. So yeah. So each time we will push, so we would push all the handles in this back here, because we have 10 of them. And then yeah, mu equals to counter.log.unwrap. So we have a counter. Yeah, so the counter is the mutex thing that we've just created. So each time we would acquire the log, we would unwrap it, and then so we can access it and then add 1 to it. And then because this is in there, so this is in the thread. So once it's done, then it would just give back the thing. Yeah, so and then at the end we'll wait for everybody here, then we can print out what's going on here. This time counter.log. So this again, this thing will give back the mutex guard, and we can deref it. Right? Is there anything that I haven't covered or mistake that I made? Now we get out of scope. Yeah, I wonder when thread finished running, so it will exit the closure, so the num will go out of scope. So release the log. Oh, but this won't compile. What have we done wrong? Use occurs due to closure. Ooh, we have. So this is moved, or what's going on? Oh, counter has been moved. Woohoo! Yes, it has been moved. So we can't call counter here. Was moved in the previous iteration of the loop. Rest is telling us that we can't move the ownership of log counter into multiple threads. Let's fix that with multiple ownership method we've discovered in 15. Let's make it more complex. So this time, we will. So instead of just like counter is the mutex, we would now have a RC reference counting to the mutex. So we combine the two things that we have learned before and make our mind blown. And this time, so this is RC clone. So these two will point to the same mutex thing, right? So pass it in here, and we do the thing. So but this time counter is still available here, so it's fine. And we don't have to deref this 2 times. I think it's smart enough to deref itself. Oh, we still have a problem. We still have a problem here. Is it this one or okay? What's going on? So we cloned it. So spawn. We unlock. Is it this one? Is it this have to be derefed? What's going on? Because counter is now a RC. Well, error message is very wordy. Here is the important part to focus on. Cannot be sent between thread safety. Oh, yes. Remember reference counting, we can't have multiple thread. The compiler is also telling us the reason why. Send is not implemented for RC mutex. We talk about send in the next session. It's one of the traits that we ensure the type we use with threads are meant for use for concurrent situation. Unfortunately, RC is not safe to use across threads. So when RC manage the reference count, it add the counter for each call to clone and subtract from count when each clone is dropped, but it doesn't use any concurrency primitive to make sure that the change to the count can't be interrupted by another thread. This could lead to wrong counts, subtle bugs that could in turn lead to memory leaks. Ooh. Or a value being dropped before we're done with it. What we need is a type exactly like RC, but one that changes the reference count in a thread safe way. So we have another one, ARC, atomic reference counting. ARC, I call it ARC. It's ARC, but ARC. Okay. Fortunately, ARC is a type like RC, but it's safe to use concurrently. The A stands for atomic, means that it's automatically reference count type. Atomics are an additional kind of concurrence primitive that we won't cover in detail here. Otherwise, it's a rabbit hole. See the standard library documentation for it if you want to know more. At this point, you just need to know that atomics work like primitive types, but are safe to share across thread. So you may wonder why all primitive types aren't atomic and why standard library types aren't implemented to use ARC by default. The reason is that thread safety comes with a performance penalty. So yes, usually we choose the most efficient one as default because not everybody's doing concurrency. You only want to pay when you really need to when you're doing concurrency. If you're just performing operation on value within a single thread, your code runs faster if you don't have to enforce the guarantee atomics provide. So just change the RC to ARC. And yeah, similar, but it's ARC. Ta-da! It works. Right. Bam, we have 10. Good. We did it! We count from 0 to 10. May not be very impressive, but it teaches a lot about mutex, thread safety. I also use this program structure to do more complicated things than just incrementing a counter. Yeah. If you're doing simple numeric operations, there are types similar than mutex that So you can look into sync, atomic, then you can look into what you can do if you want to use concurrency for arithmetics. Similarity between ref cell, RC, and mutex. Now see, so the mutex is kind of like concurrent version of ref cell, and arc is the concurrent version of RC. You may have noticed that counter is immutable, but we could get a mutable reference to the value inside it. This means that mutex provide interior mutability, and as just like cell did before, in the same way that reference cell, yep. And yeah, so they are actually working in pairs. Another detail to note is that Rust can protect you from all kind of logic error when you use mutex. Yeah, RC come with some risk of creating reference cycles, which two RC values refer to each other, causing memory leaks. Similarly, mutex come with the risk of creating deadlocks. This occurs when operation need to lock two resources and two threads have each acquire one of the locks. So yeah, so there's two resources, two locks, and then they kind of hold each other hostage. Yeah, so that will wait for each other forever. If you are interested in deadlocks, try creating a Rust program that creates a deadlock. I'm not going to do it today. Then research deadlock mitigation strategy for mutex in any language, and have a go at implementing them in Rust. To send the library, implement documentation on mutex and muteguard. Offer useful information. We'll save it for another day. Maybe after a rustling exercise or something like that. We'll round out this chapter by talking about the send and sync traits, which we can use them with custom types. Okay, last page. Hopefully this is not long. I really want to go and have dinner. Extensible concurrency with sync and send traits. So interestingly, the Rust language has few concurrent features. Almost every concurrent feature we've talked about so far in this chapter has been the part of the standard library, not the language, so yeah, you have to call it in to use it. Your options for handling concurrency are not limited to the language or the standard library. You can write your own. Woohoo! However, two concurrent concepts are embedded in the language. Is drum roll, the maker trait, sync and send. The marker trait, sync and send. So allowing the transference of ownership between thread with send. So the same marker trait indicate ownership of the value of the type implementing send can be transferred between threads. Almost every Rust type is send, but there are some exceptions, including RC, which cannot be sent because if you clone an RC value and try to transfer ownership of that clone to another thread, both threads might update the reference count at the same time. Again, RC is not designed to do that, so you can't. Therefore, Rust type system and trait bounds ensure that you can never accidentally send an RC value across threads unsafely because it doesn't have send, so it's not allowed. When we try to do this, we get an error. The trait send is not implemented. When we switch to arc, which have send, then it's fine. Any type composed entirely of send type is automatically marked as send as well. So for example, you create a struct and all of them have the same send type, then you can also send. So yeah, aside from raw pointers, then all the primitive type also have send. Allowing access from multiple threads with sync. So this is another, so remember we have the channels we can send, and then now we are talking about the mutex, which is like multiple thread access. The sync. The sync marker traits indicate it is safe for the type implementing sync to be referred from multiple thread. In another word, the type T is any type T is sync if any immutable reference to T is send. So if you want multiple access, then the pointer of it can be sent, right? So because it's distributed across multiple threads, meaning the reference can be sent safely to another thread. Similar to send, primitive types are sing. And types composed entirely of types that sync are also sing. The smart pointer is also not sync for the same reason as not send, because it's supposed to not be concurrent. The ref cell also, which is the family of cell which are also not sync. The reputation of borrow checking that it will check for the sync and know that it's not thread safe. The smart pointer, on the other hand, is sync and can be shared. So that's why we have all these things that we talked about before. Implementing sync and send manually is unsafe. You have responsibility if you do this. Because the type are made of send and sync traits are automatically also send and sync, we don't have to implement those traits manually. So yeah, nothing can go wrong if you don't do it manually. As the marker trait, they don't even have any method to implement. Okay, they don't have method, okay? They're just useless. They are just markers, basically. They're marker trait, like what it says. For enforcing invariants related to concurrency. Manually implementing this trait involves implementing an unsafe Rust code. We'll talk about using unsafe Rust code in chapter 19, almost at the end. For now, the important information is that building new concurrent type not made up of send and sync trait require careful thought to uphold the safety guarantee. So there's another thing, Rustonomicon has more information about those. Yeah, no, we're not diving into it today. This is another thing. Woo! Okay, this is about the safety thing and then the safety thing. Whoa! This is another read. I will save that for absolutely another time. Put it at the end. Okay. Summary. There isn't the last you will see of concurrency in this book, of course. In the project in chapter 20, we'll use the concept in this chapter in a more realistic situation rather than just simple example that we have used here. As mentioned earlier, because very little of how Rust handle concurrency is part of the language, many concurrency solutions are implemented as crates. This evolves more quickly than standard library, so be sure to search online for current state-of-the-art crates to use in multi-threaded situations. The Rust standard library provides channel for message passing and smart pointer types such as mutex and arc. They are safe to use in concurrent context. The type system and the borrow checkers ensure the code that using these solutions won't end up with data erases or invalid reference. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common to other languages like Python. Concurrent program is no longer a concept to be afraid of. Go forth and make your program concurrent fearlessly. Next, we'll talk about idiomatic ways to model problem and structure solution. As your Rust program get bigger, in addition, we'll discuss how Rust idiom are related to those you may be familiar with from object-oriented programming. Oh, object-oriented programming of Rust. Cool. Yeah, so concurrency in Python is quite difficult to write because, again, like, first of all, concurrency is very difficult. Second is because Python also just like get async IO standard recently. So for people who are not used to async code like me, which find it very scary, very difficult, and sometimes don't know how to debug. So yeah. But it seems that Rust already have that, because I guess Rust is younger, already have some kind of things already thought through, and also Rust has a compiler that can check your code. Yeah, so that is quite cool. But again, if you want to go to the dangerous territory, you can do so. Not me right now. And I have to have dinner. I'm super hungry. So thank you so much for going to the journey with me. I would continue when I come back from my amazing travel for Europe, for SciPy and EuroPython. So if you're at SciPy, say hi to me, please. Let me know you're watching, and yeah. And if you see me at EuroPython, say hi and tell me that you're watching. I'll be very happy if I see anybody in person and said that they discover I'm doing this online. So thank you so much, and I will see you in 2 weeks. Bye.